record. We're recording. I think I'm recording.
Yes.
Okay. Okay, so we're recording, and then I'll get the recording to you. I think with Zoom it's stored locally in my computer,
Okay.
and if it's okay with you, I'll just drop it into Google Classroom for everyone.
Cool.
So the regular induction, we want to prove that a set S is the set of all natural numbers, and there's just two conditions. Let's number those. Includes 1 and 2 if K is in S, then so is K plus 1. So if you have those two conditions, you can conclude that S is all natural numbers. And that's the whole idea behind regular induction, is that you want to prove that a statement is I guess a statement form or a predicate is true for every natural number. You just have to prove that it's true for 1 for the base case, and if it's true for some number K, then the statement is true for the next statement K plus 1.
And natural numbers are positive, natural numbers are fraction.
Natural numbers are the counting numbers.
Okay. So no decibels.
Just parenthetically, we can be flexible about this. CS people and set theorists say that the natural numbers actually is 0, 1, 2, 3, 4, 5, and so on. But it doesn't really matter. Induction works for this as well. You just if your set of natural numbers includes the number 1, and whenever it includes a natural number K, it also includes the successor, then that set must include all natural numbers. For strong induction, it's about the same. If you have a set of natural numbers okay, we can start with the base case, includes 1. The second part is a little bit, I guess, more intricate.
Where's your setups?
Oh, I'm not sure. I think they're in the toolbox, which is in the basement. Okay, maybe. Okay, so there's strong induction. Part 2 is just a little bit different. Instead of saying that K is an S, the part 2 for strong induction is that all the numbers 1 up to K are an S, then K plus 1 is also an S. And it's just a form of induction. Part 2 is a conditional statement. It's an if-then statement. And I spelled then wrong. There, I tried to squeeze N in there. K plus 1 is an S. The principle of least element is just a little bit different.
Wait, can we back up to here?
Sure.
1, 2, K is a subset of S. How is that different than sort of if K is in S?
For strong induction, we're assuming that not only is K an S, but K minus 1 is an S, K minus 2 is an S, all the way down to 2 is an S and 1 is an S. So we're assuming that there's a lot more elements in the subset S.
Okay. And how do we, and so we're told that at the beginning of the problem so that we can choose to do strong induction rather than regular?
Yeah, what you'll notice is that if you define something recursively, sometimes the recursive definition just makes reference to the one previous item. And if that's the case, then you would usually use regular induction. But in the problems that we've been discussing today, like there's some sequences that depend on the two previous items. And in that case, you need more than just the previous item. You need the two previous items. You'd use strong induction.
Okay.
And then the last one, the third one, the principle of least element. It's just the simple idea that if you have a set of natural numbers, as long as it has at least one element, then it has a smallest element.
Okay.
And it seems like an obvious idea. It turns out that these three principles are all equivalent. And if you prove something with regular induction, you could have also proved it with strong induction or the principle of least element. So let's see how it's actually used. Where do we use it? Let's see. I want a tool. Let me put a let me put a line here. Okay, that's good. And go back to text. We might do something like prove that that s sub n equals 5 to the n minus 1 for each natural number n. Okay. That's a typical thing that we would try to prove with induction. And what we're going to do then is look at, let's see. Look at this part. I circled that. That's a predicate. If we knew what if we knew what the number n was, we would be able to say, well, that equation is either true or it's not true. And so with induction, we'd want to show that the nth term of the sequence is given by this formula, but the sequence would be defined some other way. That's an example. And so we want to show
the sequence would be defined some other way.
Right. So this was one of the examples in I think in the notes. I think we had it this way: s of 0 equals 0, s of 1 is 4, and s sub n is 6s sub n minus 1 minus 5s sub n minus 2. Okay, so here's a sequence, and it starts like this. It starts 0, 4, and the next number, if you use the recursion, 6 times the previous number, so 6 times 24 minus 5 times 0 is 24. And then the number after that, oh, we went to page 2.
So sorry, I was trying to increase the screen size. Boom. Let's just do that.
Yeah, well here we should add page 2 because we're pretty much full here. let's see. I don't know how to get back into a text box, but that's okay.
Huh.
The next number would be 124.
Yeah, you double click it when you have the pointer cursor.
Oh, okay. Okay, I'll just try to align those. And then double, okay, edit text, got it.
That works too.
Okay, so here's a sequence of numbers, and it's defined not by a formula, but it's defined by a recursion. And
Okay.
computer scientists love recursion because it's a very simple way of defining it. You could even write programs that use recursion to compute something. But it's also nice if you can, instead of recursion, if you can just give a formula, just plug in the number and get the answer. But this sequence is defined recursively by explicitly given the first two numbers, and then successively, each of these is defined in terms of the two previous ones. So I'd like to show that, I'd like to prove that the nth term of the sequence is 5 to the n minus 1. And that's actually the case. 0 is 1 minus 1, 4 is 5 minus 1, 24 is 5 squared minus 1, or 25 minus 1. 124 is 125 minus 1. That's actually 5 cubed minus 1, and so on.
Mm-hmm.
So let's go to page 2 and set that up. So I'll put the definition here. S0 equals 0, S1 equals 4, and then Sn equals 6S n minus, so 6 times the previous term minus 5 times the 1 previous to that. And I want to prove that S sub n equals 5 to the n minus 1 for each n greater than or equal to 1. Okay. So one of those is a recursive definition, and then the other is a explicit formula. So if we go back to page 1, I'm going to use strong induction, and I'll tell you what the set S is. Let's, oh, this is bad. There's another S. I've used S in 2 different meanings, but that's okay. Let me change the colors. So let P of n be the predicate S n equals 5 to the n minus 1. And the thing to recognize is that if you know the number n, then P of n is either true or false. So for example, P of 0 says that S sub 0 is equal to 5 to the 0 minus 1. And that might be true or false, but we're told that S0 is 0.
Would this be the base case?
It'd be a base case.
And base cases are the sort of examples that we need to get recursion going?
That's right. Because S0 is actually not defined recursively. The value of S0 is given explicitly as 0.
Right.
Okay. So I just have to compare. Is this is S0 really equal to 5 to the 0 minus 1? Well, it is, because 5 to the 0 minus 1 is 0, and S0 is 0. So those actually have the same value. So S0 is, or P0 is true. So that was just an example. And what I want to do is this. Let me get a different color, and we're going to do something kind of weird. And okay, we're going to talk about the truth set of this predicate P. And believe it or not, what I just typed there that your arrow is pointing to says that 0 is in the truth set of the set P. So 0 is in T. Does that make sense?
Yes.
Okay. So then
The truth set is called T. Okay.
yeah, so here's the goal. Show that T is the set of all natural numbers.
Okay.
Okay.
And we are doing that because.
Okay. Okay. So that would mean that P of n is true for every natural number n.
Got it.
Which means that Sn equals 5 to the n minus 1 for every natural number n.
Okay.
And the sequence Sn is not defined as 5 to the n minus 1. It's defined in this weird recursive way. So the problem says prove that, like up at the top it says prove that Sn is 5 to the n minus 1. Well, that's that amounts to showing that this truth set is all natural numbers. So I want to go revisit the first page real quick. Look at strong induction. One way to prove that a set is all natural numbers is to prove a base case and prove the strong induction step.
And number 1 is the base case, 2 is the strong induction.
That's right. That's right. Yeah, and so 2 is the induction step, or in this case, a strong induction step. Yeah, so those are two things that we need to prove. Let's go back to page 2.
Okay.
So we need to show that, let me go back to text, and I like changing the color. I don't know why. So here's our to-do list. Base case. In this case, it makes more sense to prove P of 0 or P of 1, actually, in this case, P of 0 and P of 1 are base cases. You'd see up at the definition of S, the 0th term and the first term are actually given explicitly. And so the base cases, sometimes it's just one item, sometimes it's a couple of items, sometimes it could actually be empty and all you have is a induction step. But we want to show that 0 is in the truth set and we want to show that 1 is in the truth set. So the base case is really to show that the beginning numbers are in the truth set. And here I've already made, I've done something terrible. I'm including 0 as a natural number. When up here I said that computer science people say that 0 is a natural number, but the way I've written up strong induction and regular induction, the natural numbers start at 1. But that's okay. So that was the first thing to be shown. That's part 1. So maybe item 1, and then item 2, the strong induction step. The way it's explained on the previous page is if 0, 1, 2, all the way up to k are in T, then k plus 1 is also in T. Okay. That's really the strong induction step. Item 2, if the numbers up to k are in T or are in S, then k plus 1 is also in S. So we're trying to do a base case and the strong induction step. And another way to write that, let me write that in a different way. Let's pick a different color.
Give me a sec. You used a purple there. I'm gonna try and. If I do this.
Yeah, you got a vertical line. I'm not sure how you're doing that.
No, that's sort of trying to show what I'm doing. Okay, no, I'm trying to change the color of a specific text, but I think once you've done it, you can't change. Do you know how to do that?
No, not yet. I'll try it.
Oh well.
Let's see. This is an interesting tool, but I have no idea if we can change it. Looks like I can't.
Oh well.
Yeah. I like this a lot better than Google Meet because it has a built-in, oh no, this is BitPaper. So I don't know. I like BitPaper. It might be better than Zoom.
Oh wait, did I use the wrong color? I used the wrong color. I'm looking for a darker purple.
Yeah, I think BitPaper is good for drafting things out. And then we could go back and typeset it better. But I think I can export a PDF of this and share the PDF.
Mm-hmm.
Although this is in the video, we're recording the Zoom video.
Which is also helpful.
Mm-hmm.
Base case, strong induction step. So have we actually done anything yet?
No, we just made a list of things that we have to do.
Got it.
Yeah, actually, we did show that P of 0, we did show that 0 is in T because that's just proving that P of 0 is true. And up here, that's in the base case. But what I want to do before we actually prove things is to rewrite this. Another way to express this is to show that the base case base case is to show that P of 0 and P of 1 are true. And then 2, show that if P of 0, P of 1, all the way up to P of k are true, then P of k plus 1 is true. That's really the same thing, but expressed in terms. Oh,
gosh darn it!
You erased something. I wonder.
Oh no!
It's back.
So, more technical difficulties.
Yeah, let's see. Maybe I can grab the erase part.
Oh wait, really? Oh, nice.
Yeah. Okay. I didn't know I could do that. I feel all powerful. Okay. So
Whoa.
what I just wrote is really the same thing as mentioned in strong induction. Instead of showing that numbers are part of the truth set, it's expressed as some statements are true, or if some statements are true, then another statement is true.
Okay.
And for the base case, showing that P of 0 and P of 1 are true, or that 0 and 1 are part of the truth set T, that amounts to showing that the formula actually gives the numbers 0 and 4. And that's just a computation and comparing two values. But the big thing is to set up that induction step, and that's proving a universal conditional statement. And that's where it makes sense to write out what's a good first statement for this proof and what's a good last statement for this proof. And I think we should go to
P of k plus 1 is true.
Right, we'd like to prove that.
Right. Therefore, pk of 1 is true.
Well, if here k is a constant, k is some particular but unspecified natural number,
Okay.
and if all of the numbers 0 up to k are in T, or if all of the statements p0 up to pk are true, we just have to prove that the very next one is true. It's almost like we've lined up all of the statements. There's an infinite list of statements, and we're just going through them one by one, verifying that each one of them is true.
So then, for each natural number like k, I do not know.
Okay, imagine that we're trying to prove each of these, that the formula works for every number n. The base case is to verify that it gives the correct answer for n equals 0 and for n equals 1.
Right.
And suppose that now we're trying to prove that the formula gives the right answer for 2. We know that it gives the right answer for 0 and for 1, and we're going to try to use those facts to show that it gives the right answer for 2. And then once you do that, we know that it gives the right answer for 0, for 1, and for 2. We're going to try to prove that it gives the right answer for 3. And then the next step is we know it gives the right answer for 0, 1, 2, and 3. Let's use that assumption to prove that it gives the right answer for 4. So we're doing something over and over again. Suppose that we've already shown that the formula gives the right answer for 0, for 1, for 2, for 3, all the way up to k. Let's prove that it gives the right answer for the next number, which is k plus 1.
Okay.
So let's add a page to do that. And can we copy from one page to another?
Yeah, I should be able to.
Okay, let's copy that. And oh yeah, nice. Okay, and let's try to move this up. So there's the definition, and I'm going to write. This is the strong induction step. still care about spelling. So assumption, K is a particular but unspecified natural number, and P of 0, P of 1, and all the way up to P of K are all true. Okay. And that's the good first sentence of the proof. And the good last sentence is, we'd like to prove this, thus P of K plus 1 is true.
Got it.
Okay, and then by strong induction, we'd know that the formula S sub n equals 5 to the n minus 1 is true for all natural numbers n. Okay, so now we just have to fill in the gap. We're assuming that P of 0, P of 1, all the way up to P of K are all true, and we have to show that P of K plus 1 is true. Well, P of K plus 1, it's this. Actually, let me get a different color just to show we're doing something a little bit different. What I'd like to do is show that S sub K plus 1 equals, and I'd like to do some math and end up with 5 to the K plus 1 minus 1. Okay. That's what I have to prove, that S of K plus 1 is given by the formula. And if I can show that, then P of K plus 1 is true. Okay. But I don't know it's true because up at the top, we know S of K plus 1 is given by a recursion, not by a formula. So let me jump in here, and the recursion says that this equals 6 times S of the one previous minus 5 times the one 2 previous. And that's the recursive definition. Okay. But now, now we can do something interesting. Actually, I'm going to give some more space. S of K, well, part of my assumption there is that P of K is true. And P of K says that S sub K is equal to 5 to the K minus 1. And P of K minus 1 is true. And P of K minus 1 says that SK minus 1 is equal to 5 to the K minus 1 minus 1. And this is by
Minus 1.
Oh, I forgot the 1. Thanks. And so that's by P of K and P of K minus 1. Let's try to, yeah, okay, that looks good. So, and maybe I'll put something in here, P of K minus 1, just to show P of K minus 1 and P of K are in that list of things that we know are true. So I just used that. S sub K is given by this formula, and S of K minus 1 is given by that formula. And so that's over here, that's the strong induction hypothesis.
This, the strong induction hypothesis is
Let's see.
The insertion of 5 to the k minus 1 instead of s of k?
Let me point to it. Here's the strong induction hypothesis. It's just assuming that all of these things are true. Here's a whole list of things that are true. We're assuming that for the induction, for the strong induction step, that's our hypothesis for the strong induction step.
Okay.
In particular, pk is true and pk minus 1 is true. Okay, and let's see what we can do. Right now, you can see that now we have some algebraic expression, and I want to show that that equals this algebraic expression. So I have to do a little bit of algebra. Let's see if we can make that work. I'm just going to do some algebra, but what I have here is 6 times 5 to the k minus 6. That's multiplying through by 6. And the next one, I have 5 times 5 to the k minus 1. And then minus 5 times minus 1 is plus 5. So we're going to use a little bit of algebra and just move things around a little bit. And we can start simplifying this. In particular, this part, 5 times 5 to the k is 5 to the k. Sorry, 5 times 5 to the k minus 1 is 5 to the k.
Okay.
And then there's a minus 6 and there's a plus 5, and that combines to be minus 1. And this part, I'm going to leave that 6 alone. So I think I have this. This is, we're just combining a couple of things and simplifying it. So we have 6 times 5 to the k. We have 5 to the k that comes out of 5 times 5 to the k minus 1. And then the negative 6 and the plus 5 turn into a negative 1. And there's one thing that I want to add, that 5 to the k is the same as 1 times 5 to the k. Okay, and when I put these together, I have a lot of 5 to the k's. I can factor that out. There's a 6 minus 1 times 5 to the k, and then I still have a minus 1.
Right.
And let's simplify a little bit more. That's 5 times 5 to the 5 times 5 to the k minus 1.
Oh, and that's 5 to the k plus 1.
Right, and oh, that moved around a little bit there. Let's put it there. So in the end, I've done, I move things up a little bit. Let's move it down. Yeah, and move this there. Okay, now it looks good. So what I've done is I've proved that S of k plus 1 really is given by the same formula. There's a lot of algebra in the middle and use of the recursive definition and the induction hypothesis. But in the end, I showed that S of k plus 1 really does equal this formula with a k plus 1 there. And let's highlight it a little bit. Let's see, that's I showed that S of k plus 1 is equal to this formula, and showing that those are equal, that is statement k plus 1. Okay, and that's pretty much it.
Okay.
But it all comes down to going back to page 1. We use strong induction. I assume that the first k statements were true, that the formula that we're trying to prove is valid for the first k steps. And now we just want to extend it to show that it's true for the very next item. And that was the strong induction step.
Okay.
And from that, we can conclude that the truth set is all natural numbers.
Okay.
Let me try this. I'm going to try to stop recording right now because we're sort of done with one problem, and I'll
Yep.
post it. Is that it? No. Where do I stop recording? Stop recording. Stop recording.